So very good afternoon. Welcome to this second session of this DP. We have just join. Sir, can you actually voice new
Yes, Rudra, I can hear you.
Can you please speak we are having some echo problem. So mic, can you mute it?
What is that, Rudra? Your mic is in a very high volume, and I think that is having a lot of echo. Okay. Just maybe you may speak slightly away from the mic. Yeah. Okay.
Okay, so is it fine, sir?
Yes.
Okay, so very good afternoon to all of you. So very good afternoon to all of you. Welcome to the second session of this day 4 of the FDP. We have the speaker with us, Professor Jinto Thomas. Is associate professor in SBNI. Also, is the scientific officer G in Institute of Plasma Research and head of the laser diagnostic section. And to chair this session, I would like to invite Dr. Sunita Sahu Madam to chair the session.
Thank you, Dr. Rudrasis. Good afternoon, everyone. A warm welcome to all of you to this technical session. It is my privilege to welcome our esteemed speaker, Professor Jinto Thomas, who is joining us online for today's faculty development program. As a small token of our respect and gratitude, we would like to present this bouquet on behalf of Department of Physics OUTS.
So this is a bouquet for you, but it is virtually.
Okay. Thank you, Rudra.
Thank you, sir. Today's invited lecture features an eminent scientist whose research contributions have significantly advanced the field of plasma diagnostics and fusion research. It is my distinct honor and privilege to introduce our esteemed speaker, Professor Jinto Thomas, Scientific Officer G and Head of the Laser Diagnostic Section at the Institute for Plasma Research, Gandhinagar, and also Associate Professor at Homi Bhabha National Institute, Mumbai. Professor Thomas received his BSc in Physics from St. Joseph College, Devgiri, followed by his MSc in Physics from the Indian Institute of Technology, Madras. He obtained his PhD from the Institute for Plasma Research, with his doctoral research focused on the study of laser-produced plasmas. His research focuses on advanced plasma diagnostics for magnetic confinement fusion, particularly the development of Thomson scattering diagnostics and helium beam diagnostics for high-temperature tokamak plasmas. His area of expertise also include laser-produced plasmas, plasma spectroscopy, plasma wall interactions, laser matter interactions, optical plasma diagnostics, and laser-induced breakdown spectroscopy. Professor Thomas has published numerous research articles in peer-reviewed international journals and has been actively involved in mentoring students and young researchers in the field of plasma science and fusion technology. He has authored around 70 research publications. With great pleasure, I, on behalf of Department of Physics OUTR, invite Professor Jinto Thomas to deliver his insightful lecture on laser-based mapping of plasma parameters in fusion-grade plasmas and share his valuable insights with us. Sir, please.
Thank you, ma'am, for very elaborate introduction. And thanks a lot for making me a part of this your quality improvement program. I just wish to thank Professor Babita Oja and Rudra for inviting me for this event. So coming to the presentation, I as the chairman said that today I'll be talking about the laser-based mapping of plasma parameters in fusion-grade plasmas. Maybe a few may have visited an Institute for Plasma Research, and this is basically a view which you could probably see from the from the first floor admin building. Okay. So I was making a plan that about the fusion plasma or why we need a fusion, and then by the laser diagnostics, instead of straying into many diagnostics, I'll be concentrating on one of the most prominent diagnostics for the fusion diagnostics, which was in fact instrumental for the development of the tokamak concept itself, which I will be just briefly mentioning. Then I'll be just going more technical into the Thomson scattering and its implementation and how you can really measure a very high temperature plasma. And I'll be just showing a few slides on that. So as an introduction, what we'll be just talking about the fusion and all that. So to introduce the listeners that why do we need to have this expensive research? So we need to have some background on that. So on the screen, you can just see a graph, which is the global coal consumption region-wise, where you can see the orange color, which is basically the consumption of Asia Pacific, which is keep on increasing and increasing. Whereas for the rest of the world, you can just see that the coal consumption is decreasing significantly. So in the Asia Pacific region produces almost more than half of the global greenhouse gases because the coal comprises of almost half of its total electricity generation. So electricity generation is very essential for a country like India because we are still a developing country. So we need to grow our industry. We need to have more and more per capita energy consumption. That means that our requirement will be ever increasing. So now the burning of the coal actually worsen the regional heat wave. Then again, this heat wave triggers people to consume more electricity, and our electricity is coming largely from the coal. That means that it is acting as a feedback and it will be just keep on increasing. We are just behind China in the consumption of coal. That means that we as a single nation consumes or use more than 14% of the coal which is consumed in the entire Earth, entire globe. But at the same time, we have commitments. We committed in the recently concluded COP26 that we will be achieving a net zero emission by 2070. So net zero emission means that whatever the emissions generated in our electricity, that will be consumed or that will be just settled down by all our plantations and sea and all that one. So by 2070, we are in agreement of achieving the net zero emission. So this long-term goal is basically government broke it down to reach up to the 2070. So our immediate target, which according to its term as the Panchamitra, is that we must be having 500 gigawatts of non-fossil electricity by 2030 and 50% of cumulative electric power from renewable energy. And we must be reducing 1 billion tons of the carbon emissions. So how much? Where are we now? We are already 2027. So, well, it's not bad. At present, we have nearly 300 gigawatts of power from the non-fossil electricity, thanks to the whole general public who are just mounting lot of efforts for generating the solar power. So out of this 300 gigawatt, half is coming from the solar power. Then we have something from the wind, and we have a few quite large hydropowers. And at the end, we have a very small amount, hardly 9 gigawatts of nuclear power. And these all are basically the data and statistics taken by the PI from the PIB. But the problem is that nuclear power is too small, but without the significant nuclear power involvement, the net zero target is not possible, because the solar power, wind power, and all that basically, it is not a very robust permanent supply. Or if you need to rely on that one, that means that you need to have a large storage, because at the night you are not going to get a solar power. Wind is seasonal. So if you need to capitalize that one for the industry to provide a stable power, that's not possible. So you need to have nuclear power, more and more nuclear power. So when it is coming to the nuclear power, we know we have large reactors like Kudangulam and many other Kakrapur and all that one. But all, you see that we have 50 gigawatt of hydel power, but hardly anyone talks about that. But for the 8 gigawatt of nuclear power, everyone are aware about that, because there is a large public resistance for the nuclear fission. Now, well, even if the public resistance is not there, can we think about going? No, it's not that feasible, because we have the fuel bottleneck. Fission relies entirely on extracting finite radioactive elements like uranium-235. We have plans for enriching other things that will are just if we keep aside all that one. If the entire world is transitioned away from the coal and goes to the the nuclear, we do not have enough high quality uranium reserves to run for a few decades, maybe 50 years, if all the country is going to use the uranium. So that means that we are severely running short for the non-fossil fuel options if you are thinking about the nuclear fission. So now what? If the nuclear energy is the solution, if not nuclear fission, then it is a nuclear fusion. Now, nuclear fusion, which is less heard or less researched, or people nuclear process, it will be running to the nuclear fission. But there is a very good active research going on for the nuclear fusion. We will be just talking a little about that. So, nuclear fusion is needed because it represents the holy grail of energy. You look at the sun, star, all happening, providing the energy what the entire humanity required or entire universe required from the process is nuclear fusion. So now nuclear fusion has got a significant advantage over the nuclear fission, that the waste is very limited, or if at all there are some radioactive byproducts, that all are very short-lived, not like the nuclear fission process of few hundreds of thousands of years of life. So just briefly about the nuclear fusion, I'm sure that most of you are aware about that. So that is, it's very abundant through as it is, all the celestial bodies are providing that one. And as I mentioned already, there are no dangerous byproducts. And fusion can help to slow the climate change, because you are not going to have more, the net zero emission, that itself will be just help us in the climate change, preventing the climate change, and that is going to give you more clean air. It can reduce the conflicts among the countries, which most of the time we states that most of the wars and all basically a tussle for energy. And the most interesting part is that the fusion fuel, unlike the fission fuel uranium, The fusion fuel is considered as deuterium and tritium is available around the world abundantly. So the deuterium can be readily extracted from ordinary seawater, the heavy water, and the tritium can be produced from lithium, which is available from land deposits from the seawater. Or that means that fusion, and again fusion can power cities 24 hours a day regardless of the weather, and the fusion is produced in laboratories around the world and research is devoted to making it practicable. Now the issue is that in a laboratory fusion is demonstrated. You may be remembering that a couple of years back the LANL just showed that even inertial confinement fusion that they got a very good energy yield. So in principle, if you are thinking about the green energy, the fusion is going to be the future for all these reasons which we stated earlier. So now this is the concept of the nuclear fission and the fusion. Fusion is very well known for all, but in the case of fusion, you will be having a deuterium and the tritium, which is making the helium as well as a fast neutron of around 14.1 MeV. So where will the tritium come? Deuterium, I said that we can just get it from the water. From where will the tritium is coming? So tritium we can breed in a fusion process as a breeding blanket. So you will be having the fusion happening and the fast neutron can be just interacting with the lithium to get you the tritium. So in principle, when the fusion reactor is running, it can produce its own fuel. That means that it is a simple concept is that one. You get the seawater refined and just keep running the fusion and the energy forever. But it is very easy to say that, but there are a lot of obstacles. So now we know that if you need to fuse two nucleus, we know that the like charges repel, and the more and more you go closer, the larger is going to be your repulsion energy. So if you need to fuse two nuclei, that means that you need to overcome the Coulombic potential, and that is possible only if you can heat this material into such a large temperature where it can really overcome the Coulombic potential. So that means that if you need to heat, that means it is millions of Kelvin and a high density. And if you can have sufficiently long interaction time, the fusion is attainable. Now the talk is more about now coming to that one, how this will be done and how we will be quantifying this parameters like the temperature. So the tokamak is basically a Russian theme. I'll be coming to that one, that how that thing, so like this come into the forefront. It's a Russian, this one, like they just, the concept is that when you heat anything, that will be just expanding and more, and it will be just going and touching the walls where it will deposit energy. So you cannot keep increasing the temperature because it will be just bulging out and it will be just interacting with the material and eroding, and you will be just losing whatever the energy you want, and you will be just. So you need to confine the particle without having a physical contact with that. So that is what a tokamak does. It will be using a very high magnetic field, and when the charged particle moves in a magnetic field, that will be gyrating, and this gyration makes it not to go to the the container walls, but instead it will be always directing to the high magnetic field direction, so that you can prevent the interaction of this charged particle with the surface, and thereby it will be maintaining a very large energy for a longer time. Now there are many different concepts where you can confine that. One among that is tokamak, which we will be just talking. There are similar magnetic confinements, which is known as the stellarator, and a magnetic mirror, spiromak, plasma pinch, reverse field pinch, many things. So many geometries people were trying to get the plasma confined, and in the here you can see a very nice picture where you can just photo the plasma is photographed in a tokamak. So this is basically a torus. The center is separated by a we call it as a central solenoid, and basically this will be forming a toroidal structure. So now, as we already said that we need to measure the temperatures, which is of millions of Kelvin. Now the millions of Kelvin means that what will if 2000, 3000 Kelvin, even the tungsten is going to melt. So how do we really make the measurement? So that's a big question. And if you need the Thomson, if you need to get the plasma, you need to get almost 100 million Kelvin temperature. And that is what the temperature within the of the sun. So the big question is that how can we measure this? So normally we do measurement, we do say that the temperature of the sun is 5400 Kelvin. Okay. This basically the temperature of the photosphere where we can get the emission light. So if we can get an emission light from a body, we can get the temperature. But that is going to be from place where you can get only the emission, which is not possible always. And this emission, based on the temperature, it will be increasing and increasing to even through the X-rays level. And what will happen is that it will give me only an average measurements. You have absolutely no clue from where, what location this emission is happening. So you are going to get only an average temperature. So we can use lasers to make the measurements, and the lasers, how we can measure, you will be interpreting the temperature as a medium which is having velocity or different speeds. So now once a system is thermalized, that means that the constituent inside that system will be in a thermal motion in all the directions. And if we can measure that what is the velocity of these species, that is going to tell me about the temperature. And in the plasma, that is basically the species is basically the charged particle, and you are going to see or you are going to measure it by a laser, that is basically nothing but the photon. So if a photon is getting scattered by a charged particle, that is known as Thomson scattering, which was described or which was first invented by J.J. Thomson. And mind it, it was in 1903 where there was no lasers. Lasers invented in a much later stage at 1960 only. 1960, okay. So Thomson scattering observed from electron beam in 1963, within 3 years of the invention of the lasers. And the first application of a laboratory plasma was also in the same year with a theta pinch machine. And the first measurement of a hot plasma was made in a Russian T3 tokamak in 1969. And this measurement of this 1969 is considered as one of the major achievement or landmark measurement or landmark experiment for the fusion and the tokamak community. So this I'll start with a brief introduction about the history of this Thomson, that all were happened around in 1965, where in a conference for the in a conference, few Russian scientists gone to the UK, and they said that they have a experimental system where the temperature appears to be more than 1000 electron volt. 1 electron volt is around 11,600 Kelvin. So when they said that, the Britishers were not ready to agree on that, because they were trying many theta pinch, Z pinch, all the machines, and none of them were producing a temperature which is more than 100 electron volt. And now the Russians are coming and saying that they have. So instead of rejecting that, even at the time of the Cold War between America and between the England and Russia, the scientists were ready to take up their lasers, which was invented only a few years back, and literally they taken their lasers, spectrometer, everything, and they just shown to the mission in Russia, which the Russians were calling as Tokamak 3, T3. So the picture, picture is taken from a talk by Kodam Strip, that you can see a British scientist who is measuring the temperature with a thermometer. And this thermometer is basically the Thompson scattering system. And you can see a broken thermometer, which is just saying that there are failures of their system. And this was their spectrograph and all that. And so coming briefly into the theory of the measurement for that one. So the free electrons in an electric field of a laser will be oscillating. And this is basically the equation of motion, which appears as a electron oscillating. And whenever a radiation, an electron oscillates, that is just act as a dipole radiation, and it will be just emitting the radiation along the perpendicular direction of its oscillation. And this R, or that the scattered spectrum or scattered radiation intensity, is basically scaled by the classical electron radius R0 square. And the classical electron radius itself is so small, this means that the scattering cross section is going to be extremely weak, 10 raised to minus 30 meters square. That means that it is very difficult to get a scattered light from electron. And as the ion's mass are even much higher, there is no point of having a scattering happening from the ion. But it is possible for us to detect the scattered light from the electron, provided if you are giving a very large number of photons. That is possible only with the presence of high power lasers. But even with the highest power of the lasers, where in 1 joule of laser there are 10 raised to 18 photons, still you will not be getting much of a photon. So every photon scattering from the plasma is important for the measurement. So this is the total scattering cross section. And the scattered, if you have a plasma with a large number density of electrons, you will be getting more scattered photons. That itself is a measure of the total number density of the plasma. But if you want to know the temperature, you need to know the scattering form factor, which is a factor depending on the plasma electron temperature. These are a few plots of that scattering form factor, which is a function of temperature and the lambda. If this is 100 eV, you will be having a very sharp scattered spectrum falling on either wavelength. This I am just considering a 1064 Nd:YAG laser. And if you have a larger temperature, the peak is falling and it will be coming more and more spread. So this clearly says that if I can know the spectral width of the scattered radiation, you are going to get an information about the plasma temperature, and the total number of scattered photon is going to get you about the plasma density. Now, the scattering, there are different types of scattering based on the scattering parameters, like that basically incoherent and the coherent. If the plasma is so dense, when the laser wavelength wave is passing through that, multiple or many electrons will be oscillating together, and there will be a collective effect will be coming, which is known as the collective Thompson scattering, which is decided by the parameter alpha when it is more than 1. But in a tokamak, we will be having, there is no collective oscillations for a wavelength of 1064. So you will be getting an incoherent Thompson scattering. Now, this is a typical experimental setup. You need a pulsed laser. Because why pulsed laser? Because all the photons will be going together so that you will be able to detect. You will be getting rid of the plasma background light, and the laser will be passing through the plasma, and you collect and you disperse that one. But the problem is that if you have 10 raised to 15 number of photons, you will be getting only one photons only scattered out. And that too in the entire solid angle, with the plasma is emitting all sort of background light, and the laser light also will be a stray light. So within all this noise, we need to detect a very few number of photons, and that is what the Thomson scattering is challenging. So to overcome that one, you need to have powerful lasers, and you need to have a very good collection optics as well as the optics for delivering that. Collect as much as possible, and the the best way of detection, find appropriate spectral dispersions and the detection. You can do gating to avoid the background radiation so that the emission from the plasma will not be disturbing your measurement. Now, if you get a good signal to noise ratio in that way, then you will be able to tell that this is what the plasma electron temperature and density. Now, if you consider that there are a number of tokamak and the fusion devices are there. So this is a list of Thomson scattering system available elsewhere, and we can see that the SST1 Thomson scattering is almost coming even I am at par with many of the contemporary machines, where we can have a spatial resolution of 5 mm and a time resolution of 5.3 millisecond. Only few systems elsewhere has got a better time resolution and a spatial resolution than this. Now, this is basically a SST1 Thomson scattering system. The SST1, earlier I have showed you about the Russian tokamak. This is a much more advanced tokamak in its developmental phase. Now the development is completed. Now you will be just seeing it as a complete machine. You will not be seeing any of the complexities inside that. So this is the machine when the outer shell is removed, and you can see a number of superconducting magnets and kilometers of wires within that. The total length of this structure is around 7 meters. That means that the height of 2 floors, and the radius is around 3 meters. And this is the mission after its completion of that. Yeah. Is there any question? Rudra, is there any question? Okay. Yeah, I can continue. Yeah, I understand that. This was the setup, right? This one? Okay, 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 okay. So these are pretty large experimental systems, and hence the diagnostics are also equally large. So the thermometer which we have shown in that Russian experiment is basically this one. So this lab is basically like this Thomson scattering lab is almost a 20-meter long and 8-meter wide lab, which is kept around 25 to 30 meter away from the tokamak. So the laser will be traveling all the way through this up to the end and getting dumped there. So whatever the photons which is happening scattered from here will be just collected by the imaging system, and again the optical fiber will be taken back to the lab for the spectral dispersion and detectors. An array of feedback, alignment, cameras and all things will be just making sure that we will be able to precisely position and monitor the laser beams and all that. So we used 6 Nd:YAG lasers in place of 1 YAG. So that 6 lasers gives us the option to configure and measure the experiment when and where and whatever the way you want. If you have a less plasma density, all the lasers you pulse together so that you will be getting a single laser out of 9.6 joule, so that even at a lower density you will be able to measure. But if you have a pretty good plasma density, then you can pulse one laser at a time, so that instead of the 30 hertz, you will be getting a 180 hertz. And if in plasma there are some nonlinear physics is happening which you need to diagnose with a much more shorter time scale, you can even keep the lasers within hundreds of microseconds so that you can just do as a burst and you can study the physics there. So this diagnostics is basically to conduct physics studies within the tokamak. This is the lab setup. You can see a number of lasers stacked there, 6 in numbers, and all the beams will be coming together. And this is basically the beam dimension, and this is basically a burn pattern taken inside the tokamak. And all these laser beam will be guided by another big mirror of 6 inch in diameter to the tokamak. And this is what basically the top position where the laser will be coupling to the tokamak. You can see that a number of pico motors and cameras and lenses which is kept inside this box, and that basically going into the tokamak through this brevister window, and at the end it will be another end, it will be exiting. Now the most important thing is basically that you have a very less number of photons, but you need to collect that one. So there will be a very dedicated imaging system designed and fabricated for that, which is kept on the tokamak. And from the output, an array of optical fibers. These optical fibers are pretty large, 2 mm the core diameter. So you cannot even bend this one. So these fibers are used to guide or transfer the light from the tokamak to the lab for the spectral dispersion and detection. So these are the inside arrangements there. So the most important portion there was that when you have a very less number of photons, you cannot use a simple spectrometer to detect that, because you have only 10,000 photons. And if all these 10,000 photons are equally distributed between the pixels of a 1,000 element camera, that means that per pixel you are going to have hardly 10 photons. And these 10 photons can never give you a signal because that is just within the readout noise. So you are not going to get effectively no signal. So we just compromise the spectral resolution and use a interference filters, which I can configure the way I want with a different spectral bandwidth. And based on the bandwidth, you will be getting more and more photons. So you have a advantage that you can configure the bandwidth, high throughput, and it is going to be much more compact than a spectrograph. And you can reject the laser light very easily using the interference bandpass filter concept. And this is basically cost effective and a compact one. So we have used the interference filter polychromator, and this is what the designed and fabricated, and this is basically completely an indigenous design, our own design, fabricated within our country and operated by us. So this is basically a complete polychromator for, you can see an array of wires, and these are the wires which is required to control and bias the detectors. And these detectors are basically a high gain avalanche photodiodes, and the photodiodes we will import and the electronics we will develop, and the data acquisition and everything is our own. Now, how do we select the filter? So now this colored graph, blue color is the color for a 50 eV temperature plasma, and the red is basically for a 1000 eV. So you need to think that if you have a plasma, you will be assuming that, okay, our plasma will be, let us say, an average temperature of 500 eV. So you will be selecting the filters such that at an average temperature, you will be getting an equal number of photoelectrons, and that's the way you will be just selecting the filters for the detection for the or identification of the temperature. And the electronics is the major part, and the detector, and this you can see that a very nice nanosecond pulse which is basically detected by our detector. This is basically from a laser pulse, and almost similar signal you will be getting on a Thomson, which I will be just showing. And the detector we have developed can in principle find a 25 photo electron. That means that if you are assuming a quantum efficiency of 10 to 15 for the detector, that corresponding to around 100 or 120 photons. So the detection system is capable of detecting just 120 photons. That's basically like, it's not a counter, but everything is happening within 10 to 20 nanoseconds, and it is basically like, getting such a small signal and getting a subtracted from the plasma background also. So the detectors used are avalanche photodiodes. So we have our own lens and the electronic system, and which will be automatically making sure that whatever the collected and transmitted photon through the filter will be reaching and precisely falling within this 2.5 mm, because this setup is made like that it will be focused naturally automatically to the APD kept here. So we have earlier detectors were having much low quantum efficiency. Now the Japan has come up with a new MEMS technology detectors which can have a much higher quantum efficiency, and that will improve our detection. And this is basically the data acquisition. So you have signals of 10 nanoseconds, and if you are going to acquire, like, you need hundreds of such data acquisition channels. So it is not possible to have a complete bandwidth. So what you do is that you will be just sampling down by an integrator, so that you don't need a very high-end data acquisition system. So even this charge integrators are also developed by IPR. And finally, a digitizer basically coming from a National Instruments digitizer. Now, the most important part for the Thomson scattering is basically the calibration. So you need to calibrate each and everything. Different detectors, we have hundreds of detectors, and each detector has got its own quantum efficiency or the gains based on for a particular voltage. So you will have to calibrate each detector along with its spectral transmission and the detector response, and for each detector you need to set appropriate voltage, maintain the temperature with to a lower temperature or a fixed temperature, so that because it is so sensitive with the temperature, the gain. So if you are not maintaining the temperature, the measurement today and tomorrow is going to be different. So that will make a mistakes in your temperature estimation as well as the density estimation. And if you want to see that what is the exact number density of plasma electron present there, it's not possible for you to absolutely measure the number of photons. That's basically, it will be going to be too much of an erroneous measurement because lot of components inside that. So for that one, we will be just doing a Rayleigh or a Raman calibration. What it does is that the entire Thomson scattering system is kept the way it is required. Now only plasma, in place of plasma, you fill some Raman active gas like nitrogen into molecule and observe the Rayleigh and the Raman scattering from that. And now you know the Raman scattering cross section. You know the Thomson scattering cross section also. Whatever is the ratio between that is going to tell you exactly that how much is going to be your plasma density. So this is the interchannel calibration. We have pulsed white light source. This white light source is fed to a monochromator and then it will be just going to the polychromator, and you can just run the spectrometer easily to get a complete calibration for all the channels. And this is what the different spectral channels of the, this is basically the actual spectral calibration measurements. And the absolute calibration, you know the intensity of the Raman and the intensity of the Thomson, that will be proportional in this way. So the density you can calculate between the cross-section scaling and the intensity. So the advantage is that only the scattering species are different, so no other change. So once you did a Raman calibration, your Thomson scattering system is ready for measurement. These are the Raman lines and these are the different bandpass filters. So you will get the Raman spectrum in two bandpass filters or two channels. So what we do is that we keep changing the pressure. That means that you are changing the number of scatterers and you will see a increase in the output signal. That increase is corresponding to the like, you know, here you can just see easily the cross section. And once you get a Raman signal, we are sure that your system is ready for a Thomson signal because the Raman scattering cross section is almost 4 order of magnitude more than that of the Thomson scattering. That means that your system is now ready for the Thomson scattering system measurement. Now these all are pulsed events. So there is a number of sequence you need to follow. On the beginning of the experiment, we will decide that what is the repetition rate and the energy of the laser and all that. And around 15 minutes before the plasma shot, all the lasers will be ready for firing. 2 minutes before the laser, the internal shutter will be opening and the laser will be starting the lasing. And 2 seconds before, the safety shutters will be opening and the laser start passing through the SST1 in the pre-configured energy and repetition rate. And the DAQ will be starting the data acquisition with the, like, you know, you will have to consider what is the total delay of light which is traveling through this 30 meters, even though when we say that light speed is absolute and very fast, but for getting the signal, we need to even careful about the time distance between your detector as well as the laser, and accordingly you have to just gate it. And when the plasma shot starts, we will be getting a trigger from the main control room, and every laser pulse will be time stamped with an accuracy of nanoseconds and saved the data. And after the plasma shot, the data will be analyzed for the temperature and the density estimate. This is what a signal on an oscilloscope. You can see that this is different time at 30 hertz we have acquired the signal, and this is at 233 milliseconds you have the signal of Thomson, and if you click on the other one you will be getting a different diagram. So this signal to noise ratio is a reasonably good signal to noise ratio to have a temperature and the density estimation. And once you have that one, the temperature and the density can be estimated in a consistent way using your own developed program. And this is what the temperature estimated. So the estimated temperature for this particular plasma shot was somewhere around 400 EV. That means that 400 into 10 raised to 4. That means that it is 4 million Kelvin is the temperature of this particular plasma shot on that one. And this is way it is evolving. And this is the plasma electron density. So this is what the way we can measure the plasma parameters. So in addition to the Thomson scattering, there are a couple of other laser-based techniques also. One is the interferometry. Then there are laser-induced fluorescence and reflectometry. Many things are there. So the Thomson scattering is one of the most important diagnostics, and maybe the other diagnostics we may discuss at some point of time in later. So thanks to the team, this is basically a teamwork. These are the students and the employees who are just working for this or many other experiments within our with our lab. Acknowledging all their contributions, I'm just concluding my talk. Thanks for your time. If there are any questions, probably you can just ask the questions, or you can, if there are any deep, more in-depth questions, probably you can get to me on my email. Rudra is having my email. Yeah. You may talk bit slowly. I am getting an echo, so that's basically I am just unable to. So just talk bit slowly. Yeah. So you were saying that plasma electrons. That I understood that. Uh, when the electron reaches. Yes, yes, yes. So what will happen? Uh, the relativistic effect, okay? Like if the plasma electron is reaching to at least 500 EV, then there will be the relativistic effect will be just coming. Okay. So now what will happen? The relativistic effect, once you're reaching to around the 10 to 20 kilo electron volt, you will you will be just reaching the condition meeting the fusion. So the relativistic effect, what you will be just observing is that in the graph, if you in the calculated graph, you may be just seeing that at one location, when the temperature was keep on increasing. Yeah, this graph precisely. So you can see that when the temperature is low, this was broadening symmetrically on either side. But when I increase the temperature beyond 500, you can see that this peak of the wavelength is shifting towards the blue region. And this is basically known as the relativistic effect, or which is known as the headlight effect. What it says is that now the electron or the photons, which is moving, electrons and photons, which is moving opposite, their cross section for scattering will be increasing. So that relativistic effect is very evident here. Now, if you are asking that whether the the mass and all that one, there will be slight change in that things, and that will be affected by that cross section part. And we are not going to an extremely high situation that many other things are prominent on that. But relativistic part need to be accounted, and in principle, you will be sending a photons at 1064, and if you are reaching to a temperature of 20 keV, you will be detecting photons in the blue or UV region. Yeah, the commercial viability is a problem, big concern. Okay, so now two ways you can do. One is that the cost of the fusion need to come down, then it is commercially viable. Now, suppose a scenario that if you are not having any other way, any other energy, okay, then what will happen? Even for the available existing little fossil fuels or the nuclear fission fuel, the cost will be going quite high. So at some point in time, that's going to happen that even with any higher expenses for the nuclear fusion, that is going to be commercially viable. So now, if we are not working now to make that things attainable, even when you are ready to make a payment for that, but that is not available. So the commercial viability at present, if you are making, probably you are not going to get as cheap as coal or nuclear fission. But at some point in time, we need to compromise on that. And then this will be automatically commercially viable. And once the technology developed, always the cost will be just coming down. Yeah, so that is what the whole point I was making. It is not possible for you to have any contact measurements on the temperature. So we will be going an indirect measurement. When the temperature is high, the velocity of the species will be high. So if you can measure the velocity, you can just get the temperature. So Thomson scattering is nothing but measuring the velocity of the electrons using the Doppler concept. So we were just completely measuring the velocity, no contact, no thermometer. It is basically the thermometer was a caricature. So it's basically like the thermometer is basically the laser system and the laser beam interacting with the plasma electron.